Good morning. We are back in chapter 6. So, we were talking last time about black body radiation. This was the observation that the color of a flame was somehow indicative of the temperature of the flame. We look at a blue flame as being hotter, whereas if we have like an orange flame on a Bunsen burner, we think of that as being cooler. We also tend to see hot objects glow, and that glowing we can understand as there being some hot state that's losing energy to some cooler state, and that the wavelength of light given off is just depending on how high energy the hot state is or low in energy the hot state is compared to the cool state. And so that's where the flames are mostly coming from. The color of flames are from the transition of a hot atom or hot molecule to a cooler atom or cooler molecule, and the energy being given off in the form of light. The photoelectric effect is the effect of when light then hits metal, that electrons can be ejected, but the light has to have a high enough energy. It has to have a high enough frequency in order to cause the electrons to be ejected, otherwise there's no reaction that takes place. And so this gives you an idea that there's some step function for a metal, that if you exceed the step function, then you can have electrons ejected from the metal, and if not, then you can't. And so then the other issue gets into, well, what's the energy of the photon? Where the photon's carrying energy. This is on the next slide, but we'll see that our photon energy is equal to E is equal to h nu. This is the energy of one photon. So this was actually Einstein's contribution to the photoelectric effect, was explaining that why metals can release electrons when shined with light of minimum frequency is that metals are characterized as having an ionization energy. As long as the photon carries enough energy, then an electron can be ejected. The idea here is that your metal plus an electron can go, metal plus a photon can lead to that electron being ejected. It's as if the photon is acting like a particle. Like if that particle photon hits the metal with high enough energy, then it causes the electron to be ejected. And this is that wave-particle duality of light being seen and observed. Is that this is really the photon kind of behaving like a particle. And then the energy of the photon E is equal to h nu. Since C is equal to lambda nu, therefore nu is equal to C divided by lambda. And you can also sub in here that the photon energy can be calculated from nu or lambda, hc divided by lambda. And h is Planck's constant, 6.626 times 10 to the minus 34. Notice the units are joules times seconds, not joules divided by seconds. So this is the unit of joule times seconds. And just a reminder, the joule is a kilogram meter squared per second squared, and then times seconds. So in fundamental SI units, it would look like kilograms meter squared per second. And so then H of energy is that often states are quantized. You have jumps in energy that are required to go from one step to the next. So you need to have enough energy to go to the next step. Energy is usually not continuous. Now, where this is really helpful in understanding like the hot flames is that usually your flames are going downward on the steps. And so that you can have a flame given off when you get on one step here, or maybe you can have from the top step down to the bottom directly. You can have different photons of light being given off for each of these different steps. And if there were a continuous number of steps, then I don't know what you would expect, but it's just if we had a continuous number of steps, we would never really have states that would exist for some period of time. Here with step functions, you have kind of however long it takes you to get from here to here explains the lifetime of your state here, especially when the next step might be down to here. Okay, so if you have to imagine a step up to here, if you step up to here, you can fall down to here, then, well, however long it takes you to get here is telling you something about the lifetime of your state here. So I often say the existence of stable states that can exist, like humans, requires step functions. So it requires quantized energy levels. All right, take a look at this problem here. So a laser emits a light with a wavelength of 295 nanometers. What is the energy of this light in kJs per mole? We saw that the energy of a photon we can calculate with E is equal to h nu, also equal to hc divided by lambda. So we'll plug in our h 6.626 times 10 to the minus 34 joules times seconds times 2.998 times 10 to the 8 meters per second. Then we're going to divide by the wavelength, 295 nanometers, but nanometer and meters don't cancel, so we have to convert one to the other. Let's go nanometers into meters. 1 nanometer, 10 to the minus 9 meters. So we can work this out. 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8 divided by 295 times 10 to the minus 9. I get 6.74 times 10 to the minus 19 joules. Or excuse me, 6.73 times 10 to the minus 19 joules. Now this is the energy per photon. So the next step here is going to be solving for the energy in kJs per mole. The way we're going to get there is by starting with our 6.73 times 10 to the minus 19 joules per photon. And then I'm going to multiply by Avogadro's number. Because that's how many photons per mole there are. So we can have a mole of anything. A mole of photons is just an Avogadro's number of photons. And then 1,000 joules per kJ. If we go times 6.022 times 10 to the 23, divide by 1,000, I get 406 kJs per mole. Now, if we go back to chapter 5 for a moment and think about bond strengths, if you look at our bond strength chart, like our CH, our CC, like our bonds in DNA, about 400 kJs per mole is roughly what those bond strengths correspond to. And then DNA also in your skin and things have to actually absorb the light. So once you start getting into the deeper parts of the UV, right around 300 nanometers, your skin can start absorbing enough light of enough energy that bonds can start to have enough energy to be able to be broken with those wavelengths of light. So just something to think about on how a topic like this in chapter 6 is telling you how much energy light carries, and then you can imagine that light energy causing harm by breaking bonds within your body. And so then you can imagine a more simple question being, well, what about just breaking the bond in O2? So light of what wavelength are capable of breaking the bond in O2? So the bond enthalpy of O2 is 495 kJs per mole. And so the first thing is thinking, okay, let me think about my energy and my photon. So what the photoelectric effect is saying is that as long as my energy is high enough, then I can cause a photon, or if my energy of the photon carries enough energy to break this bond, then we should be able to break the bond. So we want the energy to be greater than this energy here in kJs per mole. And so then we want our hc divided by lambda to be greater than whatever the energy would correspond to just for one O2. Because one photon is going to interact with one molecule. So one photon plus one molecule can break the bond into two oxygen atoms. And so what's the bond strength of just one oxygen atom? Well, we'd go from 495 kJs per mole of O2 times 1 mole of O2 would have an Avogadro's number of molecules. And then let's go joules to kilojoules. So 1 kJ, 1,000 joules. So obviously this is going to be a pretty small number. So it's 8.22 times 10 to the 22, or 8.22 times 10 to the minus 19 joules. So as long as my photon carries this much energy or higher, then the bond should be able to be broken. And then if we start thinking about lambda in the denominator, if lambda goes smaller, then that's going to give me a greater energy. So I'm going to want the wavelength to be a lower number, not a greater number. But we'll talk about that in a minute. So let's actually calculate the lambda associated with this particular energy. So what photon wavelength would carry this energy is kind of the first part of the question here, one that we can work out. So the energy that photon, or excuse me, the wavelength of the photon, we're going to calculate our lambda. We'll take our h times c, divide by 8.22 times 10 to the minus 19. And we can either see that when we cross multiply lambda, that we keep the directionality here, and that lambda is going to need to be less than this. But once we get the number, we can put some more thought into this and make sure we see that we want to be lower. So 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8 for these guys, divided by 8.22 times 10 to the minus 19 gives me 2.42 times 10 to the minus 7. This is joules. This is joules times seconds. This is meters per second, so there's the per second, here's the joules, and then here's meters coming out here. And then 1 meter, 10 to the plus 9 nanometers, so times 1 E9 gives me 242. So a 242 nanometer photon carries the precise amount of energy to break the bond in O2. And then you can think about E is equal to hc divided by lambda, that if I go to an even small, oh, Siri talking again. So if we go to a lower wavelength, we go to a greater energy due to this inverse relationship. So if I go to a higher wavelength, that's going to be going to a lower energy. So I want to use a 242 nanometer photon, but wavelengths lower than that. So wavelengths lower than that carry enough energy. And again, it's all about an O2 molecule plus a photon. We have to signify h nu for a photon. Can break that bond as long as that photon energy is high enough. So this leads into the discussion of line spectra that we get for things like hydrogen. So we can have a light source. This is actually just a normal white light source. It has a narrow slit through a prism and get a rainbow of lights outward. So light usually contains a pretty broad spectrum of light. The reason why you use a slit here is so that you get a more brilliant rainbow. And you usually get a duller rainbow when you have light hitting a prism at all angles. Here we're just taking a narrow angle of light. So we have a narrow portion of light. You get a much more brilliant rainbow. But then if we do this with a different type of lamp, if we do this with a hydrogen lamp, so you can have hydrogen gas in a cell, and then you just put a high voltage electricity across it, just like you do any other light bulb. And here in this case, you take a slit into a prism, so you get a more brilliant rainbow. Instead of getting a rainbow, you get 4 distinct transitions. There's those transition here, 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 and about here if you can't see it. In fact, let me erase those. And I can kind of zoom in and you can sort of see here on the video. In the lecture room, you never see this on the slide very well or on the projector. But you can see 4 distinct transitions as opposed to a broadband spectrum. So we call these lines. So you get 4 absorption lines for hydrogen. And they specifically occur, you don't need to memorize these, but they occur at these specific wavelengths here. And so then what scientists tried to do in the early 1900s is try to figure out, well, why these four transitions? What can we learn about hydrogen? And then how can we apply that to other atoms? Is sort of the main idea here. And so Balmer discovered an equation that the inverse of the wavelengths can be found by taking some constant called the Rydberg constant and then divide by 1 minus n1 squared minus 1 divided by n2 squared. And the thing that was interesting here is that n's had to be whole numbers and not fractions. And these numbers would be returned here when I think it was n2 was equal to 2 and then n1 was equal to 3 to 6. And so when n was 3 versus 4 versus 5 versus 6, and the other one is 2, is when we can solve and determine the wavelengths on the previous page. And they would work out more or less exactly as we expected from our observed spectrum. Now, Bohr came along. Niels Bohr comes along and tries to understand and explain the Bohr model to come up with a more physical explanation as opposed to just a simple equation. So the Bohr model says, okay, electrons. So we're looking at really here by putting a high voltage on hydrogen, we're actually breaking the bond. We have an ordinary H atom. And the H atom is actually in a hot state. It's in a relatively high energy state. And then that hot state can cool off to some lower energy state. And so we're in a hot or high energy state, and we're cooling down to some low energy state. And so electrons in the lowest energy state down here, this would be the ground state. This is the lowest possible state for the atom in H. And then all these other states up here are excited states, or higher energy states, or often called maybe just like hot states. And then electrons can transition to and from. So we can have absorption of energy, so atoms can absorb energy and go upward. So this would be the absorption of energy, or they can come downward. This would be the emission of energy. And then the specific energy itself, we'll probably come back to this equation a little bit later to do some calculations with it. But we get an equation that relates the change in energy from one state to another. So the key is that we have to absorb the energy to go up, we get energy off when we come down, and that there's more than one state at the top as well. So it's kind of like that step function of, if you imagine a molecule right now, let's say we have a molecule in n equals 4. Well, it can go to 3 downward. It can go from 4 to 2, or it can go 4 to 1. And 4 to 1 has a greater energy being given off, creates a greater energy photon. 4 to 2, kind of in the middle. 4 to 3, a really low energy photon. So what do these values mean? So again, a positive delta E means energy has to be absorbed. So if we're going from low to high, that's the absorption of energy. And if we're going from high to low, then that's the emission of energy. And so negative delta E implies energy is being released. So photons being released from the energy lost in the atom. So some notes here. So the idea here is that the numbers 1, 2, 3, etc. for the H atom are corresponding to discrete energy levels. We call those quantum numbers, or relates to a quantum number of hydrogen. And energy is involved in the transfer of electrons from one energy level to another. And so the energy level can't be 1.5 or 1 1/3 or 2.5. It has to either be 1 or 2 or 3, etc., where n equals 1 is the lowest energy state. And then this works for hydrogen, can't easily be applied to other atoms other than maybe one electron ions. We don't do a lot of those comparisons, but you have to have a one electron system for this approach to work. And so then for our line spectra, actually looking a little bit closer at the equations, we get that the energy is a function of n for hydrogen. It's equal to minus hc, the Rydberg constant for hydrogen, and then the z divided by n squared. This is how you can apply this to other one electron ions. Z is just the atomic number. For H, that would be 1. So a lot of times you see here the math done on these digits here. gives you 2.179 times 10 to the minus 18 unit here, joules, times 1 divided by n squared. This equation here, or when we do the delta E for minus 2.18 times 10 to the minus 18, 1 minus our final n, so for our delta, our final minus the initial. Okay, and then the energy states of the hydrogen. This relates to the energy states and the transitions of our hydrogen atom. And so then, I think this is summarized on a slide, but I'll just summarize it here. And let me zoom in a little bit, that the transitions of hydrogen that we were seeing with the lamp were the emission, so high to low, and those were the 6 to 2, the 5 to 2, 4 to 2, and the 3 to 2 transitions. You may wonder, why are these the 4 transitions that we see for hydrogen? Well, one is that those are the 4 transitions in the visible region. So these just happen to be the 4 transitions that occur within the visible region of the electromagnetic spectrum. There's other transitions you can look at and make sense that they're probably so low in energy that they're just not visible, like the 4 to 3. That's a really low energy photon. This is actually in the infrared region. So it's such a low energy transition, it's in the infrared region. So all of the 6 to 3, 5 to 3, 4 to 3 transitions are in the infrared region. And then if you step back out and say, well, what about your 6 to 1s? All the way down to 1, your 5 to 1, etc. Well, those are all really high energy transitions. These are all UV region. So those occur, just not in the visible region, where we're looking with that prism and looking through a visible region spectra. So we have all these transitions going on for hydrogen. We're looking at the visible region photons, but the other transitions can be taking place as well. Okay, so there were all right, so let's take a look at a couple of questions here. So which transition below of an electron in an H atom causes the greatest wavelength of light to be emitted? Well, let's think about this for a minute. So this is showing us our H atom energies in this chart here. And so when you have energy lost by the atom, if you have energy from n equals 2, let's say H atom goes to n equals 1, the H atom lowers itself in energy, and the difference of energy here goes into creating that photon of light. So it's like you have your hot H2, so you have your H and n equals 2, go to H and n equals 1, energy is given off, that energy is given off to a photon. So the photon's kind of like going off into the surroundings, like our system versus our surroundings. We have our system H losing energy, our surroundings gaining that photon. Okay, so which transition allows the emission of light to be emitted is whenever we go from a high state down to a low energy state. And so we have to go from a higher n to a lower n. If we go to a low to high n, like n equals 2 to 3, this is the absorption of light, not the emission. So it can't be something like A, can't be something like C. And the key from our relative energy levels, notice that as we're going up towards infinity, that our energy levels are getting closer and closer together, that the increase in energy from one end to the next end is incrementally smaller. So we get the largest emission from n equals 3 to 2 from these choices than we do from 4 to 3. 4 to 3 is a lower energy transition, 3 to 2 is greater energy. So a greater energy photon light from 3 to 2, but we're not looking for the greater energy, we're looking for the greater wavelength. The greater wavelength is one that corresponds to the lower energy. The lower energy emission transition is n equals 4 to 3. So 4 to 3 has a greater wavelength than the 3 to 2. So lower wavelength because it has a greater energy for the 3 to 2. And then the 2 to 3 and the 3 to 4 are wrong just because those involve the absorption of energy, not the emission of energy. All right, so let's look at this problem here. So what wavelength of light is emitted when an electron in an H atom transitions from the n equals 4 to the n equals 3 level? So 4 is our initial, 3 is our final. And so This is our Bohr model equation for hydrogen atom. The energy is a function of N for H is equal to minus 2.179 times 10 to the minus 18 joules times 1 over the N squared value for the electron. Our delta E we could calculate for the transition of that energy in the H atom would look like minus 2.179 times 10 to the minus 18 joules times 1 over the final N value minus for our delta E final minus our E initial, so minus negative 2.179 times 10 to the minus 18 joules times 1 over N initial squared. Now we can factor the negative 2.179 times 10 to the minus 18 joules out of the expression. This will look like minus 2.179 times 10 to the minus 18 joules times 1 over the N final squared minus 1 over N initial squared. That's our delta E for our H atom. I think we give you this equation for exams. I'm going to double check and send out the equation sheet the next day or so. I think this one's on the equation sheet. But anyways, we can plug in our final state of 3 and our initial state of 4 into this expression. And we should be able to see that hydrogen in the 4 state, higher in energy, 3 state, lower in energy. So we should see energy being given off by hydrogen here. So the delta E for H should be negative. And so if I start with 1 divided by 3 squared, it's 1 divided by 9, minus 1 divided by 4 squared, which is 1 divided by 16. That's a positive number. So the parentheses here works out to be a positive number times a negative sign. And I think that makes sense. 2.179 times 10 to the minus 18 joules means that the H atom is losing 1.06 times 10 to the minus 19 joules. So this is the energy lost by the H atom. Oh, spent a lot of time trying to show that this should be a negative number. So the fraction here is a positive number, and then times the negative number means that the H atom is losing energy. That's why this is negative. Where does the energy go? Well, the energy actually goes in the creation of the photon. So the energy of our photon, or our photon, is kind of like a system for surroundings problem. So if our system H loses energy, then our surroundings gains a photon. And the energy is going to be like system for surroundings. It's going to be the negative of negative 1.06 times 10 to the minus 19 joules. So it'll be plus 1.06 times 10 to the minus 19 joules. So then we just take the energy of our photon equal to hc divided by lambda. We know that that photon would carry 1.06 times 10 to the minus 19 joules. And then our lambda is going to equal hc divided by that energy. So lambda is going to be hc divided by that energy. So 6.626 times 10 to the minus 34 joules times seconds times 2.998 times 10 to the 8 meters per second, and then divide by our photon energy 1.06 times 10 to the minus 19 joules. So our joules cancels, our seconds cancel. This gives us our wavelength in meters. So I'm doing 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8, and then dividing by that energy. That gives me the wavelength in meters. So that gives me a lambda of 1.875 times 10 to the minus 1, 2, 3, 4, 5, 6, and then times 1 meter, 10 to the 9 nanometers, gives me 1875 nanometers. So answer C. Okay, so what wavelength of light? So let's think about this again here. So we have our H atom losing energy. So the lost energy here goes into the creating of a photon of light. So we calculate this energy here that's lost by H. That goes into our photon energy, H nu, or Hc divided by lambda. And we just solve for the wavelength accordingly. And that works out to 1875 nanometers. So you have from high state to low state, emission of light, photons can be emitted. If you go from a low to a high, then a photon can be absorbed, or some amount of energy can be absorbed. Okay, so a quick little summary is that we have some different transitions that can take place for our H atom. We have different series that we call things. If we have the n equals 2 or higher to 1, that's called the Lyman series. So the 2 to 1, 3 to 1, 4 to 1, these are UV photons. Our n equals 3 plus to 2, so these are these ones here. The 6 to 2, 5 to 2, 3 to 2, 4 to 2, these are our visible photons. Those occur in the visible region. Now once you get 7 to 2, 8 to 2, those can take place, but those are just higher energy. Those start to get into the UV region. The Passion series, I wouldn't worry about memorizing these names. These are the transitions that end in 3, so these are in the IR region. These are lower energy transitions. So these are high energy, these are mid energy, these are really low energy transitions. And then one other thing worth noting is that you can actually ionize hydrogen if you go from n equals 1 to n equals infinity. You can actually use the Bohr model to calculate the ionization energy of hydrogen. So the delta E for the ionization energy of the hydrogen would just look like this. We would take our minus 2.179 times 10 to the minus 18 joules, 1 over n final squared minus 1 over n initial squared. The n is as n approaches infinity, what's going on here? Our n final squared as we're getting towards infinity, that this is approaching 0. And then when we start in 1, so the ionization energy for a ground state hydrogen atom is just going to equal approximately 2.179 times 10 to the minus 18 joules, because we have minus 1 over 1. So the energy it takes to ionize our H atom is approximately equal to plus 2.179 times 10 to the minus 18 joules. And then if you're curious, if you convert this into kJs, so this is per H atom. So if you multiply by Avogadro's number and then convert to kJs, that this leads this number to being 1312 kJs per mole, which is only interesting because that is actually the true ionization energy for hydrogen. So you can use the Bohr model equation to calculate the precise ionization energy for hydrogen. This is all very neat for hydrogen, but you can't do this for other elements. But it's sort of going to get us a kickstart into what it is we can learn from hydrogen that we can then try to understand how we can apply some thinking of, maybe orbital numbers or orbitals, the nature of electrons and orbitals to our bigger elements. And so some points here that the electrons can exist in certain discrete energy levels. I think that's one interesting conclusion, is that the electrons can exist in different states, but not in between the states. It's either n equals 1 or it's n equals 2. It's not n equals 2.5 or 1.5. So we have to have these discrete n values for our H atom, and that those have whole numbers and quantum numbers associated with them, meaning that they have to have those whole numbers. Energy is involved in these transitions, so each of the states varies in energy. So n equals 1 has a lower energy than n equals 2, etc. And maybe I didn't mention this so clearly, but as you go from n equals 1 to 2 to 3, what you're really doing is taking the electron as it's spinning around the nucleus into a greater energy orbit, or a greater radius orbit. So this would be n equals 1, n equals 2, n equals 3. So the radius of 1 is less than the radius of 2, less than the radius of 3. So the electron's getting further and further from the nucleus as we excite out further to higher n values. And then this works for hydrogen, not easily applied to other atoms, maybe only one electron ions like helium plus, lithium 2 plus, etc. If we want to understand bigger atoms, we're going to have to get a better picture. We're going to have to get a picture of rules. And so before we get into a discussion of, really, if you remember electron configurations and things like that, let's first talk about sort of why it is that we think of electrons as, sort of getting towards the concept of orbitals is beginning with a wave description of matter. And so, can matter behave as a wave? Louis de Broglie in 1924 theorized that light can have, if light can have um, properties like uh, the particle behavior, then maybe the particle electron can have a wave behavior. And so he demonstrated that the relationship between mass and wavelength for a particle, so this is the wavelength of a particle, not light, is equal to h divided by mv. Now this doesn't work for light because light doesn't have a mass, and so this only works for the wavelength for a particle. And so you take h divided by mv, and so as the mass of a particle goes low enough and its velocity is high enough, we get a wavelength that's interesting for the actual property itself. Let's look at one other equation before we start throwing in some numbers and calculating a few things. Heisenberg, the name I think popularized by really well by Breaking Bad, because that was Walter White's kind of alter ego's name of Heisenberg, showed that the idea here is that the momentum of a particle has a minimum uncertainty. And so then if you start thinking of the uncertainties that are required for the position and the momentum of a particle, that they have a fundamental relationship to Planck's constant divided by 4 pi. And so this here really has to do more with how well you can know the precise location and velocity of an electron, that then being known as the uncertainty principle. And what the uncertainty principle is really saying is that you cannot, at the exact same moment in time, know where an electron is and its precise momentum or velocity. And so what this is going to do, it's going to give us a particle that we don't really know where it is. And that's going to lead to then an orbital being a better description of having a probability distribution of where the particle is, as opposed to a discrete location like we might think of having, a particle. Say we're throwing a baseball from A to B, we can know where that baseball it is at each step of the way. But if we fire an electron from A to B, it's going to be like we're going to have a probability distribution of the electron as it travels from A to B. We can't really see it directly like we can maybe see a baseball. And so we have two equations here. So we have our de Broglie wavelength. Again, this is the wavelength for a particle. And then we have our uncertainty principle. Technically, this works for any particle too. Most often we see it applied to an electron, or that really the electron is the particle that's small enough and fast enough to have this behavior of the uncertainty principle really limiting how well we can know the precise location and velocity. So if we do a compare contrast, I think what's interesting is to kind of try to compare like an ordinary particle and an extraordinary particle. So like if we try to think about a baseball versus an electron here, is kind of going to be our goal for comparing our the wavelength, the natural wavelength. So the idea is, again, like think of a baseball on its way from A to B. Like we're not talking about this wave, the wave of like a curveball or whatever the pitch is. That we're not really trying to say that that's the wave that matters. We're trying to say is the baseball oscillating on way from A to B. I think you can probably agree that it's not, or that if it is, that motion isn't really important to know for the baseball. But if you fire an electron from A to B, that if we fire an electron from A to B and it gets from here to here, that it's probably going to be traveling with some natural wavelength. Okay, so let's calculate our wavelength here. So our wavelength for a baseball, we would calculate by taking h joules times seconds. We're probably going to have to break that joule down to figure out what unit we want to plug in here. We get our baseball 0.145 kilograms, so it's h divided by mv. So 0.145 kilograms is our m, and then the velocity would be for a 95-mile-an-hour fastball. Just trying to think of even a fast, but it's like an ordinary pitch. So that's 43 meters per second. Now we want to use the meters per second, and this is really just from breaking down the joule into its fundamental SI units. So kilogram meters squared per second squared times seconds. So this is the joule times seconds. So kilogram cancels, and then one of our seconds cancels, the other second cancels, one of the meters cancels. So we get our wavelength out here in units of meters. So 6.626 times 10 to the minus 34, divide by 0.145, and then divide by 43. It's 1.06 times 10 to the minus 34 joules. Or, excuse me, 1.06 times 10 to the minus 34 meters. So that's such a short wavelength that that means the baseball is just traveling in a straight line. I mean, this is just what it means to travel in a straight line. And so the baseball's not really oscillating. There's really no importance to this wavelength for the baseball. Now, what about for the electron? Let me also mention breaking down the joule, knowing to convert a mass or use a mass in kilograms here is something, if you're ever tested on this concept, that you just have to remember or have to understand is that we have to take our 6.626 times 10 to the minus 34 joules, and a joule is a kilogram meters squared per second squared. So we have to divide this into the mass of the electron in kilograms, 9.109 times 10 to the minus 31 kilograms. And then the velocity, we're just using kind of an average velocity for an electron and an atom is about 3 to 5 times 10 to the 6 meters per second. So really light, but really fast. Particles on average for our electrons, 6.626 times 10 to the minus 34, divide by 9.109 times 10 to the minus 31, then divide by 3 times 10 to the 6, gives me a value of 2.42 times 10 to the minus 10 meters. Now we have to think of atomic size in angstroms. So if you remember, 1 angstrom equals a 10 to the minus 10 meter. So, and then 1 meter is equal to 10 to the plus 10 angstrom. So 1 meter, 10 to the 10 angstrom. So multiply that by 10 to the 10, that'd be 2.42 angstrom. So 2.42 angstrom. And so the implication here is that the wavelength is on the order of the size of the atom. So if you think of an atom with a radius of about, a typical atom has a radius of about an angstrom. And so the circumference here, certainly on the order of scale of an angstrom. And so it means that our electron is actually traveling as a wave around the radius. So it's actually traveling as a wave as it goes around and spins around. So the wave-like behavior is important for the actual scale and size of the scale of the electron. So electrons are behaving as waves is kind of the conclusion of the de Broglie wavelength step, and it's behaving more like a wave than a more ordinary particle like a baseball does. And then, well, where is the wave? Can we characterize where the wave is just like any other more discrete particle we've encountered before? The answer is not so much. And so if we compare the uncertainty in the position of the baseball traveling at its sort of typical speed versus the electron at a typical speed for it. The uncertainty principle is all about the uncertainty in these particles, not the actual velocity itself. And so our velocity plus or minus the delta velocity, this is our delta V here. The V is what comes out in front. The 3 times 10 to the 6 is the velocity. Our uncertainty in the velocity of the electron would be 0.1 times 10 to the 6 meters per second. The uncertainty principle is all about the uncertainties in these values, not the values themselves. So it's all the delta x, the uncertainty in position, times m delta v. We're not uncertain in the mass of the electron. We're just uncertain in the velocity. So the particle mass is constant. Must be greater than or equal to h divided by 4 pi. And so this is our uncertainty in velocity. And so what we're using here is the uncertainty in the velocity, not the velocity itself. Okay, so if I try to calculate the minimum uncertainty for the baseball, it would be greater than or equal to sign greater than or equal to h divided by 4 pi then m delta v. That's going to be 6.626. In fact, let me just write this in here instead of writing this all out again. So we know what h is by now. I don't need to keep writing it out. So we know h is 6.626 times 10 to the minus 34. For the baseball, we're plugging in 0.145 kilograms. The uncertainty in the velocity, we're plugging in 1 meter per second. That's our uncertainty in our velocity. The velocity, the v is 43, but the delta v is plus or minus the 1, so it's just 1. We don't need to double it. We're not looking and saying it's from plus and minus 1. So the key is that the v plus minus delta v is what comes after the plus minus. So that's why we're plugging in 1 meter per second for the baseball. So 6.626 times 10 to the minus 34 divide by 4 divide by pi divide by the mass, and then divide by 1 meter per second. Negative number, screw something up. 6.626 times 10 to the minus 34 divide by 4 times pi times the mass times 1 gives me a value with just one sig fig here would be 4 times 10 to the minus 34 meters. Why meters? Well, we have joules times seconds, so we have kilogram meters squared per second squared, and we're canceling out meters per second and kilograms again, just like we did in our de Broglie wavelength. So we get 4 times 10 to the minus 34 meters. So meaning our minimum uncertainty in the position is super duper small. So for a baseball, we know exactly where it is whenever we know the velocity of the particle with an ordinary velocity. So again, we're firing the pitch from A to B, from the pitcher's hand to the catcher's mitt. And the moment we calculate the velocity with a little bit of uncertainty, because every time we take, velocity, there's some uncertainty, that we can know exactly where that baseball is with such an exquisite precision. So this means there's no practical limitation on where that baseball is. But now make the baseball an electron and give it an ordinary electron set of properties. So the delta x for the electron in the example here be greater than or equal to h divided by 4 pi. But now where our m is 9.109 times 10 to the minus 9, or times 10 to the minus 31 kilograms, and our delta v is 0.1 times 10 to the 6 meters per second. And so if we plug this in, 6.626 times 10 to the minus 34. It's really that mass being super duper small for the electron. 9.109 times 10 to the minus 34. And then divide by 0.1 times 10 to the 6. Divide by 4. Divide by pi. Let me double check this again. 6.626 times 10 to the minus 34. Divide by 4. Oh, I keep getting the wrong number here. 6.626 times 10 to the minus 34. Divide by 4 times pi times 9.109 times 10 to the minus 31. There we go. So I get 6 times 10 to the minus 10. And meters is what we get out just like we did earlier. If we convert this to angstrom, this will be 6 angstrom. And so let's think about this for a minute. So we have an electron from there's two ways you can think of this. Either the electron spinning around an atom, or you can think about the electron being fired across a potential. Either way, if the across a potential has the analogy like a baseball, where it's just like a baseball. We stop and determine at some point, okay, we have some a velocity with some uncertainty. Well, where's the particle? Well, it's somewhere in here. So it's like if you fire the electron, like you never really see the electron, you would just see like a big ball of fuzz. You would just see like a probability distribution going from A to B. Whereas the baseball, you just see the baseball going from A to B. So imagine it's almost in a way an analogy like a hockey puck. If they used to do this thing where they would actually make the hockey puck kind of like um, have a trail on it on TV so you can see it better. Well, that's what the electron would do. It would just have like a trail that would leave behind, and you wouldn't actually discretely see the particle. Is the implication of the uncertainty principle. So taking the de Broglie wavelength and the uncertainty principle together means the electron has wave-like behavior, and it's a particle that we don't know where it is. So it's going to be better described as having a probability distribution. And so what this is going to lead to is the idea of quantum mechanics and orbitals. And maybe we'll just leave here with the idea of, sort of quantum mechanics coming in to say, well, the reason why we're getting whole numbers here is, you can only have discrete number of nodes here, like 0 nodes, 1 node, 2 nodes. If you had any other number of nodes, you wouldn't get this replicating wave, and so the standing wave would break down if you had anything other than whole numbers here. And just imagine this bending over on itself around an atom, you get the same approach. So if you can imagine this from A to B on a line, just imagine it around a circle, and that's what atoms are. And that's our description, our first description of quantum numbers, is it just what maintains that motion of the electron through the atom. Okay, so I think that's probably about our time for today. So what we'll pick up next time is trying to understand not so much applying this equation, but just the idea of quantum mechanics, and leads us into quantum numbers for atoms, so we can get a description of where their electrons are, um, and get into things like electron configurations. All right, so I apologize I couldn't have this lecture in person, but hopefully you can receive this lecture, and I'm going to make some office hours for later today too, so if you guys want to meet with me on Zoom today, we should be able to do that. All right, have a great day. Take care.